Hello guys, welcome back to my channel. So today we'll be doing a different, the next type of dynamic routing protocol. It's OSPF. So it's OSPF. So OSPF stands for Open Shortest Path First. So what distance is this is actually the method by which OSPF routes traffic through its network. And we've seen distance vector protocols, RIP and EIGRP, but OSPF is actually uses completely different mechanism to route this traffic. And so OSPF actually uses what we call areas. So you're gonna have like area 0 here, and you have another area here, you can call area 1. You have another area here, call it area 2. Okay, so in OSPF design, you always have an area 0. Okay, there's always an area 0 first, and then all the other areas come. Okay, so in each area, you can have here. So let's say we have one area here, which is area 0. Okay, let's call it area 0. In each area, you're gonna have, let's say, a number of routers. You can call this one route 1, 2, router 3, 4, and so on. So each one of these routers in area 0 should have the same link state database. What's the link state database? It is information about how many networks are available on this in this area. Okay, so basically it has that information, and it has what router is connected to what router. It's all that information, what type of network, what type of subnet. Okay, so all of that is in this kind of in area 0 or in any area. Okay, so as I said, you can have other areas as well. Okay, so how does this area 0 communicate with other areas? We're going to see that in practice. Okay, so another concept of OSPF is the type of network. Okay, so the network types. OSPF network types. Okay, OSPF network types. So this is very important, OSPF, because if you're setting up a design of OSPF, you have to basically know exactly how that how the different areas are arranged, what type of area, what type of network. So basically you have what you call the point-to-point network. Okay, you have broadcast network. Okay, and or sometimes you could always call it, you can as well call that Ethernet network. Ethernet network. Okay, so I'm going to basically focus on these two. There are many other types, but I'm going to focus on this point-to-point and broadcast, because the most highly used. So what's a point-to-point network? Okay, in the first place, what's a point-to-point network? So let's say you have a router here, you have another router there. Okay, there's no other router beyond this, there's no other router beyond this. You only have router 1 and you have router 2. This is actually a point-to-point network here. It is a point-to-point network. There's no router between beyond R1, and there's no other router beyond R2. Okay. Another type of point-to-point network is if you're setting up a loopback. Okay, on, let's say, one of these routers, you're setting a loopback. So your loopback 0 or loopback 0 is also a point-to-point. Why? Because there's no other network beyond like if you want to inject loopback interface into OSPF, you basically need to define it as a point-to-point, okay? And the reason why you want to define, there are many reasons why you want to define it that way, but the first reason is that if you don't, you basically make the convergence time of OSPF bigger, okay? Because the updates sent to the link to loopback interface is going to basically asking that loopback interface, do you have other routers beyond, okay, where you are? So those updates and all of that is going to increase the convergence time of OSPF. Okay, so what's a broadcast network? Okay? The broadcast network, Ethernet network, is where you have maybe a router here, you have a router there, you have a router here. Okay, and they have some kind of a bus here. Let's call it this one a switch. Okay, so all these routers are connected this way. So router 1, router 2, router 3, router 4. Okay. So this type of network, maybe the subnet that is used here is 192.168.0.0/24. Okay. So each one of these interface here on the routers is going to be in the subnet of 192.168.0.1 here, .2, .3. So basically, this is a broadcast network. Okay, so this type of network, OSPF is going to do what called an election to select who is the designated router. Okay, who is the backup designated router. This is one other feature of OSPF that is not present in other dynamic routing protocols. So what does the designated router or the backup designated router do? All right, so we said in a broadcast network, let me say broadcast network, you have what we call the concept of designated router and the backup designated router. Okay, what does it do? Or what kind of function does it do? Okay, let's assume that this is a designated router and this one is a backup designated router. Okay, so what's their function? Let's assume that this network, all these four networks are running OSPF, okay, and this interface goes down. Okay, so an update is going to be sent out from this interface to all the routers, to here, to here, to here. Okay, so all these routers are going to hear that what happened, but none of them is going to respond. Okay, this router 4 is not going to respond, router 2 is not going to respond. The only router that's going to respond is the designated router. So it's going to respond by sending out another update to all the remaining routers, telling them, look, this interface is down. Okay, so it's like the person who is running the whole area. Okay, so it's going to send that update to R2 to R4 and telling them, look, this interface is down. Now, what if the interface that went down is actually the interface on the designated router? What happens then? What happens is that the backup designated router takes the place of the designated router. Okay, now the backup designated router becomes the designated router, and in that way, it's going to be automatic. There's no election, there's no other election. It's updates that were supposed to be sent to the designated router will now be sent to the backup to the R2, which is become the DR. Okay, so that's how it works. So I'll tell you a little bit about how the election happens. Okay, how does the routers know who is supposed to be the DR, who is supposed to be the BDR? Okay, how is the election process carried out? So when routers come up, okay, when you power on the router, the first thing you're going to do is the router is going to determine who has the highest interface priority. Okay, it's going to determine who has the highest interface priority. That's the first thing, and then the second is going to check what router has the highest router ID. Okay, so this one is going to be highest interface and we'll be able to adjust this with time. Okay, we're going to be able to see how we can manipulate the highest interface priority. So that's the first thing, criteria. And if there's a tie, if there was no interface that has higher priority, the next thing I'm going to check is the highest router ID. Okay, router ID. So it's going to check who has the highest router ID. And if there was no, if they're not able to find any router ID with the highest, if this doesn't give any result, that option, okay, is to check who has the highest loopback interface. Okay, let me check the loopback interface. I'm just trying to give you in order how it happens. So first going to be interface priority, which is who has the highest, router ID who has the highest, and loopback interface who has the highest. And then the last is going to be the highest IP address that is on each of those interfaces. Let me just say what's going to be the highest IP address or highest let me just say interface IP. Okay, so that's the criteria. Okay, the first thing is the highest interface priority, the high router ID, the loopback interface, and interface IP. So that's the process in which it's going to set who becomes the DR, who becomes the BDR. This is theory. In practice, you're going to see it's very much clear and much simpler to do than explanation. And generally, in my videos, I try to bring out the practical part of it. If you really want to, if you're really interested, just in the concepts, there's a ton of information on YouTube where you can actually get a lot of more solid concepts. Okay, the next concept about OSPF is what we call the OSPF timers. Okay, so when OSPF router comes up, that router is gonna wait at least it's gonna wait 40 seconds. Okay, and then after 40 seconds, if it doesn't hear back from any other neighbor, it's gonna declare itself as the DR. Okay, that's how OSPF works. And if the router came up and found another router, okay, this R1, R2, if there's any found another neighbor, so what's going to happen is, let's say the second router came up after the first one. What's going to happen is that now this is the DR. Okay? Now since this is the second router and there's no other router after that, it's going to be the BDR. Okay. And another thing you have to understand by default, when you bring up router on OSPF, okay, you add another router to that OSPF. By default, it's going to assume a network type of broadcast or Ethernet. Okay, that's why it elects the DR and the BDR. Because with the point-to-point, there's no election of DR and BDR. Maybe I didn't mention that one. But, by default, when the OSPF routers come up, they're going to assume that they are running on an Ethernet segment. Okay, so they're going to do an election where they elect the DR and the BDR. So this is going to be the DR, this is going to be BDR because he came up second. Okay, and another thing is, if this one is the DR, this one the BDR, even if it has a higher router, a better router or higher router priority, it cannot take over the, once the election has happened, it cannot happen again except something goes wrong. Okay, it's only when an interface goes wrong that, in this case, this one is going to be the DR until the other one comes up, or if whatever, just so once we have a DR, we have a BDR, it stays that way for that segment. Okay. And then the next timer is called the hello timer. Okay, the hello timer, which is by default 10 seconds. Okay, so what's a hello timer? So basically, when two OSPF routers are up, every 10 seconds they're going to send an update, okay, to the neighbor to say, okay, I'm here, are you there, are you there? So basically to know if the other router is available, is online. So they're going to send updates every 10 seconds. And so after the fourth update, okay, which is 40 seconds, after the fourth update of hello, if they don't hear back from the other neighbor, they're going to declare that neighbor as dead. Okay. So if the neighbor is dead, maybe that's when maybe an election has to happen this time, or if there's a BDR, if it's a segment that has BDR, DR, and other routers, then the BDR, the DR is going to send that update to all the other routers in the segment. So that's how OSPF works. So now let's talk about the OSPF metric. Okay, OSPF uses a metric called cost. Okay. So that's the OSPF metric. It's called cost. And what does cost do? It runs the highest. It runs that's a method by which OSPF uses the best path through its network. Okay. And usually for higher bandwidth, okay, higher bandwidth, one interface usually indicates a better cost. So bandwidth is very, very important factor in the calculation of OSPF metric. And the algorithm that is used for OSPF metric calculation is called the Dijkstra. Okay, the Dijkstra algorithm. All right. As I said, we're going to see a lot of these concepts while we're doing the practical. So right now I'm going to clear the screen. I'm going to bring up the router. Just going to clear the screen. So I'm going to bring up one of those routers. So I'm using EvenG. So basically I'm going to bring up two routers here for them. 1, 2. All right, I'm going to bring up these two routers. Let me just rename them. So we have two routers here. I'm going to add another. I'm going to add another node, but I'm going to add a connection to the internet. Okay. So then call this internet connection, iNet connection, and it's going to be with the management type. So the icon, let me use something like this one. All right, so let's put all of this together. I'm going to connect this one to the internet. Okay, 0, and then on the gig 11 of R1, I'm going to connect to gig 01. Gig 01 of R1, I'm going to connect to gig 01 of R2. Okay, so that's going to be our first network that we're going to set up. So now let's power this thing up. Okay, and as I said, this one is going to come up. This one, I'm going to power them together, but when we enable OSPF, we're going to make sure that we enable, we're going to power one device first, and then the second device. So let's power this on. We'll power this one on as well. Of course, OSPF is not going to run until we actually enable OSPF. So when we enable OSPF, whoever is enabled first is going to be probably the, it's going to be the as long as the second one is not enabled within the first 40 minutes, 40 seconds. So I'm going to open the console. R1. Open the console for R2. So I went ahead and powered the two routers, and also I put the IP addressing for the segment. So the gig 00 is going to be DHCP facing the internet, and we're going to have a loopback on each one of those routers. So loopback 0 for router 1 is going to be 1.8.8.1. Okay, I specifically use 1.8.8.1 because if not, it's going to conflict with some other configuration that I'm going to be doing on this setup. So the links between routers is going to be this format. Okay, it's 192.168 and XY. So X is going to be one router, then Y is going to be the other router to the side. So XY. So in this case, it's going to be 12. So 12.1 and 12.2. This for the interface, and then for loopback. Router 2, as I said, is going to be 2.2.2.2. All right. So let's get into the configuration. Just going to lower this out. All right. For R1, I configured the loopback interface for R1. I'm going to have to configure now the gig 00. Gig 0.0. Let's say no shot. And IP address is going to be DHCP. This is the interface that's connected to my home, to my home router. So it's going to get an IP address from my not from my home router, but from the VM router, from a VM virtual machine that's directly attached to my home router. Okay. So yeah, from the EVNG DHCP server. So the IP address 192.168.186.144 has been obtained from my DHCP server on gig 00. Now I'm going to configure the interface gig 01. And short address is going to be 192.168.2.1. Alright, as far as IP addressing is concerned, I think we're done with R1. So IP3. Okay, so yeah, so we have our IP addresses, they're all interfaces are all up. Now we're going to do the exact same thing on R2. On R2, terminal interface, I'm going to start with this loopback 0. Address. Loopback interface, we don't have to just say no shutdown. The loopback interface should always be shut down by default, except you will physically shut them down. So when you're configuring loopback interfaces for the first time, you don't actually need to do the not shut. So IP address for this loopback is going to be 2.2.2.2. Okay, we did that for as well. So interface gig 0/1 short. Okay, IP address is going to be 192.168.12.2. Okay, so for R2 as well, we have our IP addresses configured. Give that configuration. If I save for R1, save. Okay, so if I do show IP interface on R2, you can see our gig01 is up, our loopback is up. So what is left is to first of all, let's come back to R1, see if R1 has access to the internet. Okay, so now it has an IP address, but does it have access to the internet? If I do ping, let's say I ping the my gateway, which is 192, or just ping internet. I'm just gonna ping like 8.8.8.8. Okay, ping is working, it's good. So we have access to the internet on R1, and even if let's say we lost traffic, no, it should only be for the directly connected interface. So access to the internet is available only on the gig 00 of R1 until we actually allow some kind of routing on this router. On this router, we cannot be able to source traffic from the gig 01 to the internet. Let's actually try it. I do source loopback 0. Oh, that one works. Okay, look, source 01. Okay, yeah. Well, that makes sense. I think it's just for the directly connected interface, but not for, let's say, traffic coming from R2. That one's not going to work for sure. 100%. It's not going to work. So, anyways, so right now, what's left? We have to enable OSPF. Okay. So up to this point, we don't have OSPF running neither on R1 nor R2. So the first thing we want to do is to, let's say, go into R1. Okay, configure terminal. We're going to say router OSPF. Okay, we give a process ID, which is locally significant. By the question mark, the process ID. Let's call this process ID 1. We're going to use 1 all along, just to make things simple. Even if we use process ID 2 on router 2, doesn't really make any difference. But for simplicity, we're going to use process ID 1 all along. Okay, process ID 1. Now, next thing is we're going to do the router ID. Okay, so what router ID we're going to give to this one? We're going to give, let's create the question mark. Okay, so it's asking for router ID. I'm going to give this one 0.0.0. Okay, what that means is that if there's a router ID which is 0.0.0.2, that router with router ID 0.0.0.2 has preference in the OSPF election, DR and BDR selection. So we're going to put this one as router ID of 1, and we're going to make sure that R1 is a DR. Okay, we're going to make sure because we're going to enable OSPF first on R1 and make sure that we wait more than 40 seconds so that R1 actually assumes the DR, becomes a DR, and then we enable OSPF on R2. That's what we did in the concept. So, okay, so after doing that, next thing we want to do is we can now already actually advertise OSPF, okay, on the, because right now, up now, OSPF is not running. Okay, it's not running. So for OSPF to run, we have to say network. I'm going to give the network 192.168.12.0. Okay, if I do question mark, so it's going to ask for wildcard bits. So wildcard bits is 0.0.0.255. Now next, it's going to ask for the area. Okay, so as we said, OSPF runs in areas, so we always start with the backbone area, which is area 0. So we're going to call this one area 0. Okay, and that's it. Now there's one more interface that we haven't advertised, and we're going to advertise that one right now. So to advertise that one, I'm going to do exit from here. Okay, I'm going to go interface back 0. Okay, and I'm going to say IP OSPF network. Okay, if I do question mark, we have several options here. We have broadcast, we have non-broadcast, we have point-to-point, point-to-multipoint, we have point-to-point. Okay, as I told you, OSPF types, there are many. We're going to focus basically on point-to-point and the broadcast, which are the most common. Okay, but so you also have the non-broadcast and the broadcast. So for the loopback interface, we're going to call it point-to-point. Okay, and the reason why we want to call it point-to-point is that there's no network beyond the loopback. Okay, there's no network beyond the loopback. So if we don't call it point-to-point, we advertise that network like a broadcast. Okay, what that means is that the convergence time for OSPF is going to be longer because there's going to be link state advertisement sent out on this interface, okay, on the loopback interface, to whenever let's say a link goes down. Okay, whereas if it's a point-to-point, there's no DR or BDR election taking place, so it quickly converges, and yeah, so that's the purpose of using point-to-point on loopback interfaces. We're going to do exactly the same thing on R2. So at this moment, let's check what's going on with our OSPF setup. Okay, if I do show IP OSPF, okay, question mark. I could say, okay, OSPF neighbors. Let's check. OSPF neighbors. Okay, so IP OSPF neighbor. Okay, it has no neighbor, and with good reason. It has no neighbor because this router is not up yet. When it's going to be up, it's going to this router 1 is going to see router 2 as a neighbor. So at this moment, router 2 doesn't run OSPF. It's only router 1 that's running OSPF. Now we've gone past 40 seconds, so we can now check if router 1 has elected itself as a DR. Okay, how do we check that? We can just do show IP OSPF interface gig0. Okay, let's check what it says. Here we're going to say what kind of network is it? What kind of OSPF network type is broadcast? As we said, it's a broadcast. There's only a cost of 1. Okay, and if you go a little bit down, we're going to see what type of okay, it elected itself as a designated router. Okay, right here we can see it elected itself as designated router. Okay, and maybe we could also see something about the timers. So the timers, we have the hello timers, 10 seconds. The dead timer is when it sends 4 hello timers without no response from the neighbor. It's going to declare the neighbor as dead. Then we also have this wait of 40 seconds we talked about in the beginning, whereby when OSPF comes up, it has to wait 40 seconds to see if there's another router in the network. If not, then it declares itself a DR. That's exactly what router 1 just did. Then we also have the retransmit of 5 seconds. I have to double check exactly what that means. So yeah, so these are the timers here. And what we're going to do, we're going to enable OSPF now on our router 2. Alright, so on router 2, I'm just going to say configure terminal. I'm going to say router OSPF, okay, process 1. We said we're going to use process 1 all along. Then we're going to add a router ID. Router ID for this one is going to give a higher router ID. Okay, 0.0.0.2. Okay, now we're going to advertise one network. We're going to advertise the network 192.168.12.0. We're going to use the subnet. Then the wildcard fix is 0.0.0.255. Then we'll give the area. Give the area of the area 0. Okay. I just noticed now that there's a network, the loopback interface. Okay, the loopback interface was advertised on router 1 as well, but okay, all right. So So right now you can see there's an adjacency that's been formed between R1 and R2. Okay, we just saw a message here. So this adjacency is being formed right now, but we haven't advertised the loopback interface of R2. Okay, so I'm just going to go say exit. Go to interface loopback 0. I'm going to say IP OSPF network point to point. Okay. Alright, so what happens? I define the network type, but I actually did not define. I did not advertise the loopback interface. Okay, so I'm going to go into network. So the loopback interface network type is point to point, but the network itself was not injected into OSPF. So I'm going to go here. I'm just going to say router OSPF process 1. Let's say network is going to be 1. But 2 is going to be 2.0.0.0. Okay. And the subnet, and then the wildcard bits, we can use this one, 255.0.0.0. Okay, and we say area 0. Okay, we're going to do this exact same thing on router 1. Router OSPF process 1. Network is gonna, right here is gonna be 1.0.0.0. Okay, and I'm going to explain why the wildcard bit is a little bit different here. I just want to put on these two routers, and I'm going to tell you exactly why. There's 255.0.0.0. Okay, so what does that mean? What it means is that 255 here, this bit here means this bit can change. Okay, the second octet here means this bit cannot change. Okay, this one means this one cannot change as well. This one cannot. So only the first bits can change. Okay, the same thing here. The first bit can change, but all the other octet. But the first octet bits can change, but the other octet bits cannot change. That's what this wildcard bits meant here. So in the sense, when I was advertising the gig 01 interfaces, okay, the wildcard bits, if you check here, what that means is that all these other bits cannot change. Only this one can change. Okay, that's what it means. Practically, that's what it means. Okay, so how do we actually calculate wildcard bits? It's a different topic. But I'm just trying to let you know. If you see here, wildcard bit is 0.0.0.255. What this 255 means here is that these octet bits can change. Okay, but these other ones where you have 0 here, which matches this one, means this we have to leave it that way, cannot change. And so yeah, that's how we advertise it. And now we have both loopback interfaces advertised into OSPF. Okay, no, I should add area 0 here. All right, so after doing that, I'm going to go out here and let's see the magic. So if I come to R1, I do show IP route. Okay, you just say route OSPF. All right, so from R1 we could see that it formed it can actually see the loopback interface network R2. Okay, and the reason it doesn't see directly connected is because the directly connected it is directly connected, so it doesn't see it as an OSPF network. Okay, the 192.168.12.0, it's directly connected. That's why it doesn't get injected into OSPF. Okay, so that's it. What that means is that if I do ping, let's say if I ping 2.2.2.2, and I source my traffic from loopback 0, okay, of R1, that thing works. Okay, in the same way, if I come to R2 and I do ping to 1.1. What was that? For loopback on R1 was 1.8.8.1. Okay, and I source my traffic from loopback 0 of R2. That thing should work as well. So what if I'm trying to, okay, by the way, if I do AP OSPF interface is 0, okay, let's see what it gives. Okay, it tells us that this interface has formed, it formed a neighbor relationship with R2, and the broadcast type link, first one, and that this router R2 was selected as a backup designated router. Okay, so if R1 goes down, R2 is supposed to be the DR. That's what it means. Okay, so if I do IP OSPF neighbor, okay, so that's exactly what I was trying to. Yeah. So now you can see there's a neighbor relationship formed between R2 and R1. Okay, and then we have a backup. We have it's in full state, which means it's fully converged, and we also have a DR. DR has router ID of 0.0.0.1. Okay, and then we also have a dead timer. Okay, you can see here it can never go beyond 40. Okay, so it's the 39, and then it goes back to 0, and then So yeah, that's it for OSPF. That's it for OSPF first video. We're gonna have an expansion of what we did today on the next video. And for now, thank you for listening, and then talk to you next time.